We all hear about biomass as a key part of the renewable energy puzzle, right? Turning stuff like wood chips and farm waste into power. But there's a bit of a hidden challenge that comes right out of the smokestack. So let's dive into the fascinating tech that's designed to clean up our clean energy.
And that's really the big question, isn't it? When we burn biomass, yeah, we get energy, but we also get, well, something else. The road to truly clean energy doesn't just stop at the furnace. In a way, that's where it really begins.
And this stuff right here is at the heart of the problem. It's called fly ash. Just think of it as this super fine, powdery residue that's left over after you burn something. And figuring out how to get all of this out of the air before it hits the atmosphere, well, that's a massive engineering challenge. Okay, so let's get into why this is such a complicated issue. It turns out not all biomass is created equal, and that makes cleaning up the exhaust surprisingly tricky. Now, what's really wild about this is just how much it varies. Take a look at wood compared to rice husk. Burning rice husk can produce something like 10 times more ash than burning wood. What that tells you is that a single one-size-fits-all filter system, it's just not going to work. And it's not just about the amount of ash, it's the size of the particles themselves. Depending on what you're burning and how hard that boiler is working, you can get this huge range of particle sizes. You've got these bigger chunks, and then you've got this super fine dust, all mixed together. And each of those needs a totally different strategy to catch it. So how do you even start to clean this messy mix? Well, you begin with the industry's workhorse, the first line of defense against those bigger particles, the cyclone separator. The design here is just brilliant in its simplicity. I mean, there are no moving parts sitting in that hot gas stream. It's basically a really carefully shaped steel cone that spins the exhaust gas at incredibly high speeds. The heavier ash particles, they just can't make the turn, so they get thrown against the wall and fall down to be collected. All right, let's walk through it. First, the dirty gas is pushed into a spiral, which creates this powerful vortex. That spinning motion generates centrifugal force, which flings the heavier ash to the outside walls. From there, it just slides down into a hopper. And the cleaner gas that's now in the middle, it actually reverses direction and spirals right out the top. Simple, but super effective for that coarse dust. So here's the bottom line. Cyclones are popular for a reason. They're relatively cheap to build, they can handle ridiculously hot gas that would literally melt other kinds of filters, they're super low maintenance, and they collect ash dry, which makes it much, much easier to handle. But cyclones do have a weakness. They're not great at catching that really fine dust. So to meet modern air quality standards, you have to bring in the high-tech stuff, the solutions designed to capture those tiny little particles that manage to escape. One way to do it is with a wet scrubber. The whole idea here is to move the solid particles out of the gas and into a liquid. You do that by spraying water into the gas stream. The tiny ash particles collide with and get trapped inside the much heavier water droplets, which are then really easy to collect. Now, a totally different way to think about it is the electrostatic precipitator, or ESP for short. This is pretty cool. It uses a powerful electric field to give all the ash particles a negative charge. Then, these newly charged particles are naturally attracted to positively charged metal plates, which literally pulls them right out of the gas stream. So you've got two completely different philosophies here. The scrubber uses water, and you end up with this wet slurry you have to deal with. The ESP uses electricity and collects the ash dry. But a really key difference for the people running the plant is the pressure drop. Scrubbers need a lot more fan power to push the gas through, and that means more energy. So what happens when the environmental standards get even tighter? Well, that's when we move into advanced filtration. This is where engineers have developed these next-generation systems that take these basic ideas and push them to near perfection. And this is a fantastic illustration of a major leap in cyclone tech. On the left, you've got your standard cyclone, where the gas has to make that sharp 180-degree U-turn. But on the right, that's a VORSC tube. You see how the gas flows straight through? That's way more efficient and cuts down on the turbulence that lets the fine dust get away. The real secret sauce for the VORSP is something called a scavenge flow. See, instead of just letting the dust fall out because of gravity, a separate, smaller fan is used to actively suck a little bit of the gas and all that concentrated fine dust right out of the system. That one simple trick dramatically boosts how much of the tiniest, most difficult particles you can capture. But when you need to get as close to zero emissions as humanly possible, there is one final option: the bag filter.
Think of it like a gigantic, high-tech vacuum cleaner for the whole boiler. It is the ultimate barrier, but man, it comes with some serious risks.
And this is exactly why it's a last resort, especially with biomass. You can get glowing sparks coming from the boiler that can literally set the fabric bags on fire. Or if the gas cools down too much, moisture can condense and turn all that ash into a sticky, cement-like sludge that completely clogs the filter. It's incredibly effective when it works, but it's also incredibly high maintenance. So let's just put it all together real quick. You can see all the trade-offs pretty clearly here. Cyclones are simple, but they're just not as efficient. Scrubbers use a ton of water, and you get that slurry. ESPs and VOSP systems, on the other hand, give you high efficiency, dry collection, and lower maintenance than either scrubbers or those tricky bag filters. Okay, so we've spent all this time talking about filters and all this amazing cleaning technology, but what if the best way to clean the smoke is to just make less smoke in the first place?
30%. Get this. According to some estimates, that's how much fuel could be saved in a typical palm oil mill boiler just by using full automation to perfect the combustion process. 30%. And this, right here, is the biggest takeaway of all. The most powerful, the most cost-effective way to control emissions isn't a filter at all. It's a smarter, more efficient boiler that burns the fuel so completely that it just creates way less pollution to begin with. So the ideal strategy, the winning combination, really becomes a step-by-step approach. First, you perfect the fire with automation. Second, you use a tough, high-efficiency dry system like a VOR sept to catch what's left. And then, only if you absolutely have to, you add that final stage fabric filter to get to near zero. Which really leaves us with a fascinating final thought, doesn't it? In this whole quest for cleaner energy, maybe the most elegant solution isn't about building a better trap at the end of the pipe, but instead, learning how to build a much, much better fire.